So I've turned on the recording, and it's over to you.
Okay. Can you see my screen?
I can.
Okay. Okay, let's begin. If you have any question, you can ask me.
Just one thing. Jeeping, could you speak as loud as possible?
Okay. Sorry. Wait a minute. I close the window. Okay. Today our goal is we want to show if we have homology theory, reduced homology theory. We want to show there is an isomorphism to the further to the cell homology of this is a CW complex. And then we have with coefficients in abelian group G, and then also it can be isomorphic to the singular cohomology. Okay, this is the goal. Okay, so first maybe we can recall some definition about what the so-called reduced homology theory. A reduced homology theory just as a functor from pointed double complex to the abelian group, and there is one more isomorphism. Is the sorry. Okay, star isomorphism to star plus one. So suspension.
Firstly, it's a functor from somewhere to graded abelian groups. So
okay,
we have
okay.
Just not just one abelian group. We have
yeah.
In general, countably many.
Yes, because there are many. This is the index number.
We also need some version of the excision property.
Yeah. I just write such that it should satisfy the 3, maybe 4, or 3. First is called homotopy invariant Austrian. That means if you have to homotopy map to the double complex, pointed double complex, such that F1 homotopy to F2, then you will get in the abelian group they are equal.
Okay, so we actually don't need excision for reduced homology, but we do need long exact sequences.
Okay. Second is exact means. If we have a vibration then you will get to the home of the map, and then you will get sorry, not E. You will get exact sequence. Maybe I can take another page. Okay. Third condition is
there's
okay.
one more group which is missing in this sequence. There's another arrow which goes to k-1 of A, and the whole thing should be exact.
Yeah, because something.
Or let's think. Or maybe it follows from the configuration sequence for spaces. Let's think.
Okay. This is X. It's the cone.
So we have this. This is the starting few terms of the configuration sequence. What's the next one?
Yeah.
Jipping, what is the next one? What is the next term? Yes, and it's homotopy equivalent to which space?
Yeah, this is homotopy to X attention A. This is homotopy to suspension of A. Yeah, because
okay. Well, this part is clear. Well, yeah. I think. But then let's just note that if we identify Kn of sigma A with Kn-1 of A, we get the using the suspension isomorphism, we get a sequence which can continue indefinitely in both directions, to the left and to the right. And the exactness follows from the exactness of a single Kn plus the suspension isomorphisms.
Yes, because you have this, you can add another exact sequence on the left or on the right. Then you get a non-exact sequence. Okay. Any question?
Okay. Well, there's a similar definition of a non-reduced homology theory, and similar for cohomology. There's a reduced and a non-reduced version of cohomology, and in fact, one can pass from each of those to every other version. It doesn't really matter which one we consider. And there's another remark. We don't actually need spaces to be pointed in order to define reduced homology.
Okay.
But there's a pointed version and the non-pointed version, and they determine each other.
Okay. So should I continue?
Well, I don't know. What do people think? Are there any questions? Well, it looks like there aren't, so yes, please continue.
Okay, and it should have another condition. Wedge should, let's see, if X is a wedge product, then you have isomorphism from the K star xi to K star x. Okay. I see some other reference. This is the additive. If a homology theory satisfies this, is called the homology additive. Okay, but here I will use this.
Okay, well, there's a stronger version of the wedge axiom, which requires the functor to commute with, well, let's say arbitrary unions of sub CW complexes. In this particular case, we have a wedge, which is the union of its summons, but sometimes it's it's well, most cohomology, most homology theories satisfy the stronger version, which basically means the homology commutes with some type of co-limits in the category of spaces, more general than wedges.
Oh yeah. Okay. Thank you. Okay. So the our goal is to show ordinary homology. So ordinary homology is, say, we have one more condition called damped. So zero is the coefficient with Arbinian group G. Yeah. Okay. So first of all, we want to show our goals. Maybe I recall. First, we claim this part. Yeah. Okay. Oh, sorry. So now X is the pointed CW complex, and maybe not right. For each n, we have the cell. We can write E alpha is index set. This is the n cell, and we write X is a skeleton, and we can recall the is generated by the free Arbinian group. Generated by Dear. So first of all, we can prove there is a lemma one. For each n, there is a equivalent. Maybe we can call it kappa n from the. This is the object in the bin group to the CNX times G. Okay. And K X you attach X n minus 1 is 0 if M not equal to N. Okay. So this problem may be more easier because you know there is the isomorphism from Km xn quotient xn minus 1 to you take the wedge product of x just by you quotient the xn minus 1 part in xn, it will look like the some wedge product of sphere. Yeah, this is just by the you construct give a CW compact cell structure. So we just need to check this part isomorphism to CNX tensor G. Okay, and we know this part is equal to the direction Km. So just by the wedge product issue. So we can just give explicit map from the C cross C to the project to co-products. I just take mu, you have alpha, you have G, and then you take every bit from G alpha is this is just G if beta equal to alpha. If it's 0, if beta not equal to alpha. And it is easier to check this isomorphism. Because if you have an element from here, you just take to the to one generator, because this is a free Abin group, you can take to the generator to CNX, and you can check this is isomorphism. Okay, so actually, sorry. So the kappa n is this side. Kappa n, you can consider kappa n as the follow composition of the following map first from the x to kn wedge product, and then you go to kn, then you go to the cnx. Okay. Maybe we can call this is mu, because in the next we will use this map. Yeah, and yeah. Okay.
Are there any questions? Anyone? Well, let's continue.
Okay. Okay. Now we want to show a property. First is the reduced cohomology of xn equal to 0 if I am larger than. Second, the map from xn to xn plus 1 is epimorphism. Third,
Okay, so what is k? Do we assume the dimension axiom for k, or we don't?
k?
Yes. So do we assume that k satisfies the dimension axiom?
Yeah. This is an ordinary cohomology.
Okay, so please note, everyone, that we assume here that k has this extra property, which means the cohomology of or homology of the zero sphere is zero outside degree 0.
Yeah. Zero is 0 equal 0. Otherwise, yeah. Oh no, this is not 0. This is G. Sorry. Okay. So this is so the map from xn to xn plus 1 is epimorphism, and this is the ordinary homology to the x is isomorphism. Maybe we can give this map a name IN. Sorry, IN star, because the IN is inclusion from x to x. Okay. So
isomorphism in the last part, isomorphism for which m?
Sorry. If n less than, sorry. Okay, let's go. We have the non-exact sequence as before. We talked about km plus 1 x m plus 1 cosine x to km xn to km xn plus 1. Okay. Plus one quotient to xn, and from the first lemma, we can recall the first lemma. Okay. I have another step I didn't prove in the first lemma. This part. Sorry. And yeah, this is a very easy fact because you just follow from this, follow from this here. Yeah. This is very easy because it's the next step is just the sum of m minus s of 0. Yeah, and here k is ordinary homology. If m not equal to if m not equal to n, they will vanish. They will equal to 0. Okay. So from the first lemma, we can see if I'm not equal to n and I'm not equal to plus 1, I start I need to give a notation here. I start and if I'm not equal to n and I'm not equal to 0, the two part is 0. So this map is isomorphism. There are nothing to see. And if m equal to n, you can see this. So if m equal to n, you can see this part is equal to 0. So this is R star is epimorphism. And similarly, if m equal to n plus 1 is monomorphism. Okay. Any question? Okay, let's begin. Let's continue. So no. So this part we have proved. We can show this part is this part is we just need to prove the first and the third part. Okay. If maybe we can take it. This is what we want to prove. If m larger than then by the a star, we call a star. star is epimorphism, we can get the KMX isomorphism KMX minus one. The isomorphism to KM just want this is equal to 0. So the most difficult part is the third part. So if I'm less than. Any question? Okay. So this is what I want to show. If I am less than, so we will have the this we can degree by 1. So I mean you can show this isomorphism for some R, for any R, not for some R. So here we have a commutative diagram which say you consider this one. So you consider direct limit to R, and here is this map is reduced by the inclusion. I think it's R or maybe R. Yeah. And this is by the also by the inclusion. Yeah. This is a collection of morphism, and this is just you take x to okay. So if we want to this is isomorphism, it's enough to show this part is isomorphism. Okay, so maybe this is the most difficult part. So maybe I can give maybe not coloring, maybe another property to show this part is isomorphism.
Okay. Let's assume for a minute this map is an isomorphism, and
Yeah.
let's prove it later.
Okay. If we assume this is isomorphism, you will get this is isomorphism. So you will get this answer. Okay. So what we have? So we need to so we have proved this property. No, we need to prove there is a differential from the two. Okay, correct. Not prove. We give a differential from the k x minus x minus 1 to k minus 1 to x minus 2 because we want to prove this. So So now we want to show there is a differential, because here is also differential, and here we also need a differential. This is just given by the non-exact sequence we have talked about. Firstly, for x and cos x and so on, you can to x minus 1, x minus 1. No, sorry. You can go to xn minus kn minus 1 to xn minus 1. And why we have this map? Because because this is xn union xn. And we can go to another part. It's xn union xn minus 1 union xn. This is suspension xn minus 1. And then you take the ordinary cohomology. This part is
well, the easiest way to define delta would be to interpret or triangle, doesn't matter, would be to interpret the source and the target as relative homology groups. For example, kn of xn mod xn minus 1 is the same as kn mod xn minus 1, the non-reduced version. And same for the right hand side. So we are able to use the long exact sequence of the triple xn minus 1 xn minus 2, and the delta is just the connecting homomorphism of the sequence.
Yeah. So this is just we take the projection stuff. Okay. Oh, so we have proved. Let's recall what we have proved this isomorphism to the CX tensor. This is the number 1. So so here we have a differential map from xn minus 1 mod xn minus 2. This is cn minus 1. So here we will get a differential on the chain map, on the chain. Just by definition, you can define the map D, because we have the dart map. Okay, so we recall the notation. The notation. This is we call the kappa n x, because in the next we will use this notation. We will recall here. This is the kappa minus 1. Question? Sorry? Okay.
No, this was nothing.
Okay, so there is a easy observation. You can see D composed D equal to 0, because this one is equal to 0. Why this one equal to 0? Because you just by definition to equal to P star star then star partial star. Okay, we have maybe we can recall the non-exact sequence. We can ensure here part of the P star is equal to 0. Maybe we can recall here. So we just add another piece partial star. This is 2. Okay. Minus 2. Yeah, minus 2. X minus 2. So y p star, y partial star p star is equal to 0 because you have this exact sequence. Yeah. Okay. So now we want to prove the homology theme. Yeah, we have those. We have construct the chain and the dimension of the chain. We want to show the homology theme. Okay, let's compute the homology. Theorem said there is a isomorphism from the, maybe we can see star here. I see dot. The differential isomorphism to K star X for into. Okay. So we have C. This is the homology of the P and X and crucial it's minus 1. So it is enough to show this is isomorphism. Okay. Any question? No. Okay. How to show this is isomorphism because we have a community diagram. Maybe I can copy my community diagram because there are, if I write down this part, it will take more time. Okay. Why this diagram commute? Because
Okay.
this part.
First of all, does everyone understand what is written in the diagram? So maybe it's worthwhile to explain the rows and the columns. Well, there's just one column.
Non-exact sequence.
And where does the red column come from? Where does the blue row come from?
Maybe I have. Sorry, this is partial star. I can explain this because this is just the exact sequence here.
Yes, so the red column is just the long exact sequence of the couple xn, xn minus 1. Nothing, no surprises there. And similarly, the blue one is what? The blue arrows in the middle come from the long exact sequence of what?
The blue one is you take okay. I need to. This means there is a map from xn to xn plus 1.
Okay, so the blue one, the blue row is part of the long exact sequence of the couple xn plus 1 xn. Very well.
Yes. So sorry. In the sorry, this is notation because maybe I have never introduction this notation, but sorry, maybe you confused. Yeah. Okay. This part is just by the definition of third, and this part is also by the definition of third. And this part is in the first property I have proved. Yeah. This is in the I think this is the third column. So the property I have proved. You can see. Yeah. This is I have proved. Maybe not proved, but we assume this isomorphism, so we'll get the isomorphism. So this is we actually do in the property 1. Okay. So now we need to compute something. So if there is a boundary, no, first the k x coach x minus 1. If is a cycle. If in cycle, this means dot 0. So dot is p star dot is p star partial star p star partial star d equal to 0. So then you use the p star z is here, partial z equal to 0. We want so partial star and the compound p star is z is equal to 0. And and by the P star is uh, uh, monomorphism because this is zero. So partial star z equal to zero. So then you use the long exact sequence of the red column. You will this is partial star z equal to zero. So it must be in the image of P stars. So maybe I should be so 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 see in the image of paste. This star means that here. So we get so P star gave a morphism isomorphism from the boundary from the cycle to the this one. So right here, P star is the isomorphism from the cycle. Okay. So next, I want to check the code cycle. So I can clean this part. I just this is isomorphism. So if C is a boundary, it, it's a boundary. That means you can find C prime. Yeah, C prime in sorry, C prime. And then you use start is partial star C star P star. So you will get Z equal to P star partial star Z. This means then you use the long exact sequence, the blue one, blue long exact sequence. You will get Z in the P star kernel G and plus 1 star. Then you use the isomorphism. This is isomorphism. So the kernel of this one is exactly the kernel of this one. Okay. So you will get Z equal to the P star, the image partial star. Okay. So P star now define isomorphism from the boundary. Okay. So now we get show the exact sequence. The first is the kernel and star by P star. And this is the KNII. This is the P star to the cycle. So you this both isomorphisms, so will get sorry, this is zero. So you will get our theory. Let's see. So this is not a big P. This is the ordinary homology. You get the ordinary homology is exactly the homology of this guy. Homology of this guy. Okay.
Okay, so we basically proved the statement that the cohomology of the cellular chain complex is the same as sorry, the homology of the cellular chain complex with G coefficients is the same as the homology of X, where by homology we just mean an arbitrary theory which satisfies all the axioms plus the dimension axiom.
Yeah.
Very well. Well, it follows from by basically by inspecting the diagram on the previous page that everything is functorial with respect to cellular maps of CW complexes. A cellular map is a map which takes the N skeleton to the N skeleton for every N.
Yeah.
But there is one assumption. We did use the fact that as n goes to or m goes to infinity, the direct limit of the homology groups. Sorry, as r goes to infinity, the direct limit is of the homology groups is k m of x, where r is the number of the skeleton.
Yeah.
And we have this this isomorphism and a similar one for cohomology. And well, since we still have a lot of time, let's prove them all. But let's start with the easier of the two, the one for homology.
Okay.
Так, значит, для всех, кто следит, понятно ли, что происходит? Так, ну хорошо. Very well. So yes, let's first do the easy case and then the more complicated one.
Okay. So I want to ask, should we explain this differential map is exactly the differential map in the you use the cell complex define the differential. I mean, in ordinary theory you use cell and cell, and you will get the differential just by some degree. And actually, this is the same to the degree. Is the same. Should I explain?
Well, yes. If you have if I have it prepared, then yes, let's see.
Yes, because we just definition by the dim map by at the dart, and actually we don't see what is the DMAP explicit look like. So I will prove this. When I prove the isomorphism, I mean, when I prove this theorem after, I will explain the differential map is exactly the ordinary differential map. Okay. Maybe we can take a new page. Okay. So we see another property. That means we here are x are also quantitative of the context, and what we want to prove? We want to prove the limit, direct limit of the cohomology. Maybe we can because we have used only here. We have used only here. We use another number. We want to prove this is isomorphism for cohomology theory. Actually, there is a similar story. See, this is not isomorphism for general cohomology theory. But I will see when I prove the homology case.
Okay, just one remark. It doesn't matter that we consider xn to be the nth skeleton. We could consider an arbitrary filtration by sub CW complexes, but this filtration, in order for the proof to work, it needs to be parameterized by the natural numbers.
Okay. So we give a little notation here. IN, as before, IN is inclusion to S, maybe not S skeleton, but you have S subcomplex to X, and the G is inclusion to from Xn to Xn. So we want to prove the where the homology. Okay. Here we use something so-called telescope. Okay. First, we construct the telescope by the smart product. Actually, this is inclusion is contained in -1 to infinity, which smart product to X. Yeah. And first, we want to see its X prime and X have the same homotopy group. The first thing I want to explain. Okay. Okay. give some notation.
Jiping, Mikhail has asked you a question in the chat.
Okay, sorry, I can't see the chat. Which one? Node cross product.
In the definition of X prime, you have the sequence of such product.
Not smart. This is a smart product, not the
I see.
product. This is white product.
Okay, of course.
Okay. I didn't see the cross product because this doesn't smart product. It look like you need to do a quotient. Look like this one. And here you need to go on and you need to glue the base point. Yeah. Maybe this might look like this. Yeah. Then you quotient the zero case. Yeah. Okay. Sorry. Okay. Maybe I can. Okay. Okay. And now I want first explain the fundamental group, not the fundamental homotopy group. X is equal to homotopy group of Xn. I need to get some notation here because the notation is there some notation here. So this is just by the restriction. And you have the this is just by the restriction of the for project that doesn't look very look like the you restriction the projection. Yeah, because the smart products it like you take a product and you quotient by something. So here I write the product. So, and we need to define the Xn prime. What is Xn prime? This is look like the union of the L. This is L 0 to L minus 1. You take a smart product with XL. Yeah. And it's easy to see this is the subset of X prime. Yeah. Then we use the same notation here. This is like and you also have the notation maximum prime to maximum. This is also the restriction of the projection. Sorry. maybe we can copy this part because yeah, I can get small in the next page.
Okay, well, it's it's more or less clear that the telescope is summatively equivalent to x.
Yeah.
Okay, so in about 5 minutes we will need to have a break.
Okay.
So shipping, it's up to you where we stop.
I think I have another notation. I have didn't introduction here. Maybe I think I can finish the notation here.
So you you want to prove another lemma? Is this correct?
Yeah. I want to prove because this is not very hard. Yeah, maybe 5 minutes or 6 minutes. Yeah, maybe. Sorry, I think 10 minutes is enough. So we have one. I just I'm sorry.
Jipping. It's very hard to hear what you're saying. Could you please speak a little louder?
Okay. Maybe this is my iPhone technical. So after break, I can get more information. Sorry. Okay, sorry. So we have another maybe we can another notation here. Here I write Kn, but you need to think this is not the homology. Yes, I am very sorry. So this is not a homology. This is just a map because here my homology is notation by Q. Homology is notation by Q, not by N is by. This is just you take x to x. Yeah. This is just you take x to x, and there are some facts. Yeah. Maybe easy fact. You just take some composition map. Yeah, this first is compose Gn prime equal to Gn compose and compose Kn equal to x. So yeah, this is a very easy effect. And compose R equal to R. So R compose I and prime. And there is maybe this next is not easier, but you need to see more. Kn compose Rn home topic to Ix prime. I can see this part because this part is not easier here. Yeah. Actually, you can get this home topic map just by you take maybe I can first because I can see a diagram. So R is xn prime to xn, then you compose with xn prime. Yeah. Here, this is and xn prime like you take a product, something product, and so the home topic map is given by So just given by you take S X and this is T to 1 minus T X plus T X for S in the here n minus 1 to n and x to x in x and t in 1 0. So this is the homotopy map. So now you can get R is a homotopy equivalent for any. Yeah. Okay, so we have or maybe we have the following diagram. Let's see. You consider the direct limit. This is by the star. Okay, here I also use the star in the homology function. And in the homotopy group to this R star to pi q x star. This is the R prime star to pi q x prime star. This is R star. What I have shown, this. What I have shown, this one is isomorphism. Yeah, because it's a homotopy equivalent. And actually, if you can show these two parts are isomorphism, then this question will done because this diagram commute and you will get this is isomorphism. Yeah. So the question is how to show this two part is homotopy. This blue part. Yeah, I think this is also very easy. Yeah, because xn is just like the subcomplex of x, so you can check the morphism is I can see some sketch.
Okay, so this is called the compactness argument. We have a co-limit of with basically an increasing sequence of subcomplexes and on the one hand, and the union on the other hand, and the image of every map from a sphere to the union is completely contained in some finite subcomplex xn, and ditto for homology for homotopy between any two such maps.
Yeah.
So this is standard. Let's do two things. Let's assume that the telescope is homotopy equivalent to x. And secondly, let's have a break, and then we'll continue.
Yes. So you have break. I will test my effort.
Okay. Other questions? Well, very well. So let's have a break, and then we'll continue in 20 minutes.
Okay.
Okay, where's the chat?
Enough power. Yeah, okay. Very well. Sorry. So I have for the homotopy group of x prime and x are the same. So the next, I want to prove the limit of the well, the homology theory is equal to the ordinary homology theory. Okay, so let's take the telescope and take two parts of the telescope. First is you call it A. This is by definition is union of the odd number in L odd number L minus one L U wedge product no smash product XL, and this is one subset in X prime. X prime is the telescope, and you have the another part is you take the even number, and this is another part in the telescope. So easily you can see to reflect the union A and B equal to X prime, and the intersection look like you just intersection in the whole you just intersection in the every x. Yeah. You just look like you just take this as the intersection. So the intersection is the wedge product of the L cross XL is isomorphic to L XL, and you also can see that A and B are also a strong deformation retraction. Yeah. No, not A and B. You take this part. L is old. Take XL. This in A. This is a strong deformation retraction. Okay, similar for even case. Okay, so now we can use the Meyer-Wittery sequence. Okay, take a new page. So we use a Meyer-Wittery sequence. We have the KQ is a ordinary homology. A intersection B to the plus KQ in KQB, and then you take to KQ. This is the A union B. A union B is a telescope. So, and we can see this part is by the isomorphism I have mentioned. This is the wedge product, and then you use the wedge assume. We can get this is KQ X with XN, and this is KQXN. Yeah, this is you take old and you take even part, take old part. This also same thing. And this is isomorphism. This is isomorphism to KQX. So this isomorphism just by we have proved the homotopy group are same. So this induced by the, if you remember, this is the same notation for homotopy group, and this other by R star. So now we get this is, we can give a notation this F prime beta prime, and actually if we write down the F prime and beta prime, we will get the result. Actually we can take a sum here. I mean, we can take a minus n. Then you will get the ordinary thing I will prove. So this is okay. The same thing. You take the sum here. So here you can easily to check the definition of prime. The definition of prime is you take x to, because you know how to take this part. This is you know, you from a intersection B just to A and just to B. So maybe it's minus B, sorry. So this is x plus, if you remember the notation, this is for x in KQ x, and when you take the sum, when you apply sum, you will get f x is exactly the x minus g n plus I star x for Cmax. So actually, this is a definition of the, when you define the direct limit, this is the what's the definition in the direct limit. So, and you can show this it actually is monomorphism. Is monomorphism. And nice, sorry. And the Cohomology is exactly the definition of this is just a better definition. There is nothing to. So actually these are also monomorphism, and you can also show, you can also write the what is the beta prime. Actually beta prime, I can no place to write down what is beta prime. Okay. Beta prime just take the elements. You take every comment. Maybe you can give n. If beta n prime is just the minus n I n star x for x in k x. So you can easily check this is also isomorphism. So here is a isomorph. Here we have a isomorphism map in the KQX to the coconut of. Actually, coconut is just the definition of the direct limit of KQXN. So from this diagram, we prove the theorem that is the KQ x is equal to limit Okay. Any question? Okay. I will continue. Maybe I can see the cohomology part. Okay, for the cohomology,
Well, maybe for the cohomology part, it's worth just pointing out the differences between
Yeah.
between this part and the easier homology part. By the way,
Yes.
we well the only real difference is that the direct limit is exact, whereas the inverse limit is not in general exact. So
Yes.
where exactly did we use this the direct limit statement in this proof?
Which one is exact? So
Well, the direct limit functor is exact on basically
yeah,
abelian groups and on more or less any category which has a forgetful functor into abelian groups, but not all categories, more or less all. For example, for topological abelian groups, the situation is different. Anyhow, we don't want to get into this. We want to use we want to see where this proof uses the exactness of the direct limit.
Here I just compute the direct limit just given by the co-kernel. Yeah.
And
Because we have the short exact sequence.
Okay, so we have the union of two things. The unit is X, and the intersection is comprehensible. So we okay, so we have the exact sequence on at the top, and then the one in the middle. Why? Why do I have zeros on the left and on the right of the one in the middle?
Because you can check the alpha or alpha prime just monomorphism. Yeah, just you have the definition of alpha prime.
Well, to prove that we do have zeros, it would suffice to prove that either alpha prime is injective or beta prime is surjective.
Yeah.
So which one is easier to prove?
Inject. Alpha
Okay,
prime is injective.
Let's prove it.
Okay. Rf is x minus c plus 1 star x. Therefore, x in Q. So if of x equal to 0, that means alpha minus g and m square x equal to 0. But this part is in the KQ xn plus 1. Yeah. Yeah, because you just take x to the one part is you take x to the x, and the other part is to the n plus 1 case.
Well, I don't understand.
Okay. Maybe I should clearly, because alpha is isomorphism from KQXN to KQX. And you from this x to one is x, another is here is minus g n plus 1 star x. Okay. Yeah. Maybe I should apply here in inclusion. Yeah. Sorry. Maybe this is clear. The Rn just xn kq to sum. Yeah, you just to the n splits. Yeah.
And why
So
why do we get an injective map? Please note that for cohomology, the analog will not be surjective in general.
yeah. In the
So,
cohomology case, yeah.
there is something about direct sums as opposed to direct products, which allow which enable this argument to work.
Yeah.
We want to understand what exactly it is.
You mean you have a short exact sequence? Maybe you have here you have a limit a to limit c, then you need to continue the limit 1a, limit 1b. Yeah.
Well, if by lim you mean the inverse limit, then yes. If you mean the direct limit, then there's no direct limit.
This is
One
should be
at
there.
least for not for a billion groups.
Yeah.
Anyway, so let's look at the maps again and see whether or not it's possible to spot the exact place where we where the argument gets complicated for cohomology and is straightforward for homology.
Okay. Maybe we can see the homology. Cohomology.
Maybe
Cohomology.
maybe it's okay. Well, I think it's more or less the same sort of proof for
Okay.
well, the same amount of effort which it takes to prove the injectivity of alpha or the surjectivity of beta.
Yeah. For the cohomology, you have the diagram. This is the this is also A and B. This isomorphism to the product Q minus 1. And this is this one. Next is maybe we should continue some part. No, I think this is enough. This is product, and this is product. No, not product. Okay. These are also isomorphism, but here we have no short exact sequence. We have no short exact sequence, and
well, we do have a short exact sequence. It's just a little longer than the one we had before.
Yeah. So this map you take this map is yeah, this is the same thing. This also has the same as homology case.
Well, not quite. The formula is the same, but in one case we have the direct sum, and in the other case we have the direct product.
Yeah. Yes, they look like this one. Maybe have some number here. Okay. Okay. So for homology case, we have done, but for homology, we have. I think we have. Do you for cohomology case, you have, then you will get the short exact sequence 0 to limit 1 to the KQ, maybe KQ, to the limit, yeah, to 0. So.
Well, basically, what you said in the beginning was correct. The alpha for homology is injective.
Yeah.
And the proof, the proof is straight from the formula. If you haven't checked this, then just let's move on to cohomology. For cohomology, we have this exact sequence, and we want to identify the image of alpha with lim 1 and the kernel of beta, which is the map on the right, with lim 0. So how do we do that?
So for homology, this is just as this is maybe this is a co-kernel of alpha. This is no, this is KQX. This is the kernel. Yeah.
Yes. And now we want to see why those kernels and co-kernels are related to the inverse limit and to its derived functors.
Yeah.
Well, there's just one.
Yeah, the co-kernel here, the co-kernel is the inverse limit. Yeah. It's inverse limit. Okay. Yes. And the co-kernel is co-kernel lim1. Sorry.
Yes, but why? Why is the kernel why is the kernel equal to the inverse limit itself?
In the inverse limit, you need to satisfy this condition for the KQX to KQXN. Yes, because when you define the inverse limit, there is a subset of the product and satisfies they have the transition function and satisfy the like this one.
Okay. Are you
And
are you going to explain what the lim1 is?
yeah, the lim1 case is you have the definition of lim1. Just as as a co-kernel, maybe I can see more generally, but I just want to think the homology case. So sorry. Maybe more generally, we have some product from GI to some product from GI, and the definition of limit is like you take limit r first, you take every gi to gi minus some if is the map from gi to gg. Maybe this is the gi plus 1. This is the gi. Okay. And the limit you define as the inverse limit you define as the kernel of the R, and the co-kernel you just define as the lim1 direct limit.
Okay. Well, this is correct, but well, sort of correct. But we don't see from this definition where does where this these notions come from. So there is a functor lim,
Yes.
which is defined on which goes from the category of all countable sequences of abelian groups with homomorphisms going from the one with a greater index to the one with a lower index, and the functor lim is for better or worse not exact. It's by the way, is it right exact or left exact?
Left exact.
Well, let's see. Well, yes, I think you're right.
Yeah.
It's left exact, and so we want to consider its right derived functors. One of which is well, the first of which is the lim one, and well, by general nonsense, the well, it makes sense to talk about derived functors in this case, and so we basically we define those functors, and it turns out that there is lim 0, which is lim, and there's lim 1, which need not be 0. And so the formula on the right at the bottom is a recipe for calculating lim 1. It's not the definition. It's a recipe for calculating the answer.
Oh, okay.
Okay. Well, let's now see how this all helps us to calculate the to prove that the homology of the n skeleton and of the whole complex is isomorphic in degrees n minus 1 or less.
Okay.
So this all was to prove something about the homology of a complex and the homology of a skeleton. So far, everything works for an arbitrary increasing sequence of subcomplexes labeled by natural numbers. We didn't really use the skeleton in this case, but but we wanted to prove something about the skeleton and the limit. So let's see how this helps.
Okay. I have. So I need to prove the monomorphism of R.
state on one of the previous pages something about the cohomology or homology of a CW complex and the cohomology of the skeleton. Tripping, do you remember? Basically, there was a map, IN lower star, something like that, and we wanted to prove that if if we have an ordinary cohomology or homology theory, then the map is an isomorphism.
Yes. This is IN star.
Yes. And so let's assume that everything works, that the statement about limits and the inverse limits and direct limits works. How does it help us to prove that the map IN lower star is an isomorphism and degrees lower than n?
If IN star is isomorphism, then
No. We want to prove that it's an isomorphism.
Yeah, we want to prove this is isomorphism.
For Q less than n.
Yes.
So for Q less than n, the map IN lower star is an isomorphism. So how do we prove this?
We know. No. There is nothing. This is isomorphism if
Yes. So no. We don't know this, but if we take xn and xn plus 1, then we show that the map is an isomorphism. So for and the same for n plus 1, 2 n plus 2, and so on. So all maps starting from the one going from xn to xn plus 1 stabilize, which means the direct limit is actually kq of xn. On the one hand, on the other hand, it's kq of x.
Yes, this is a KQ with the x plus something bigger.
Okay, so this works for homology. How does this work for cohomology? For cohomology, we have maps in the opposite direction.
Yeah. You have the
but they also stabilize, meaning all maps starting from the one going from xn plus 1 to xn are isomorphisms.
Sorry.
Yes, so all those maps and and so on from xn plus 2 to xn plus 1, they're all isomorphisms. So well, two things happen. Well, first of all, since the maps stabilize, the inverse limit is again just kq of xn.
Yes.
And what about lim1? Well, by the Mittag-Leffler theorem, lim1 vanishes. Why? Because well, since the maps stabilize, they satisfy the Mittag-Leffler condition.
Yeah. Because it satisfies stabilizer, so you
Okay.
use
So we proved what we wanted to prove for both for homology and cohomology. Namely,
yes.
we proved that an arbitrary ordinary homology or cohomology theory coincides with singular homology, respectively cohomology. Are there any questions? Jiping, do you have any questions?
Yeah, I have the last question. So I also want to construct the spectral map. Yeah, but today, this week I have another talk, so I have enough time to think about this.
Well,
So
basically, one proof is enough for one seminar.
Yes.
There's another way to prove at least the cohomological part of the result, but it's not completely for free because we need to construct a map of spectra or at least a homotopy class of maps and well, it's not very difficult, but it still requires some work.
Yes, I think there is some answer online. They said if X is represented ordinary cohomology theory, then you will get. I don't think this is true. You will find enough large n and the pi n xn equal to g and pi n plus k xn equal to 0 for any k. For any k in Z. Is this right?
Yes, but this does not determine the spectrum. Well, for example, we have the structure maps in the definition of the spectrum, and well, first, the first requirement is that the omega version of the structure maps must be an isomorphism. Okay, so then the spectrum one gets is an Erlenberg-MacLane spectrum, but still one needs to prove this. And
Okay.
just knowing the homotopy groups is not enough. We need to construct a map going in one direction or in the other direction.
Okay.
And one advantage of the elementary method is that we get the result both for homology and cohomology, using more or less the same type of arguments.
Okay.
If you want to proceed via spectra, then there's the cohomology case is straightforward, more or less.
Yes, yes.
But the homology case is slightly trickier.
Yeah,
Basically, let's not worry about it. I think we've spent enough time on this already, it'll do.
Yeah.
But Jipping, do you understand the proof that you have just presented?
Yeah. I just need to add this part in my notes, I think. Okay. Yeah. I think I can type down my notes and get a tag version. So if I have time, I think I can finish.
Okay. Otherwise, just send me your notes as they are, and I'll if you don't mind, I'll post them on.
Yeah. Of course. But I think can I give my notes later, because I want to give a typed version, not a write version, so not a handwriting version. So maybe
It's up to you.
yeah. I think it is. I want to give you a formal version part, and I need a little time to write down the formal version part. Yeah.
Okay.
Maybe I can send you the script, data right, and then I will give you a formal version. Okay.
Okay. When you're ready.
Yeah.
Okay. Jipping, thanks for your talk. For anyone listening, next week there will be a talk by Arshak about model structures on the categories of spectra, and how exactly we get the model structure such that the weak equivalences are precisely the maps which induce isomorphisms of the homotopy groups. Okay, so let's.
Okay.